Very pleased to have Mike, who came from the nearby Tokyo National Institute for Informatics, and she will talk about FPT algorithms, right?
Well, yeah.
Okay.
So my talk is about an FPT algorithm for directed multicut with 3 terminal pairs. But it's basically a talk about the combination of a lot of very powerful tools that recently arose around fixed parameter tractability. And it's joint work with a lot of people, as you can see. Lars Jafke, Paloma Lima, Tomasz Majarek, Marcin Pilipczuk, Boani Sharma, and Manuel Sorge. And this is due to the main part of this research happening during the Power workshop that is organized by the Warsaw group. So this is how we all came together to solve this problem. And it's about the directed multicut problem, where we are given a directed graph and a set of terminals, a set of terminal pairs. That's important, right? So we have a start vertex and a corresponding end vertex. And we are asking whether we can find a set of bounded size, of size at most k, such that if I remove the set from my graph, can I hit all the paths that connect to corresponding terminal pairs? So if I remove the set S from the graph, can I afterwards, such that I can afterwards not find any path anymore between Si and Ti. And this is known to be W1 hard for a while already, since 2014. And there's a few cases that can be done in P, not so many. This is first of all for DAGs, so for graphs without directed cycles. If we don't have directed cycles, then we can do it in P. Also, if we do not care about this correspondence between start vertices and end vertices, then we can also do it in P. So if I want to find a set that just cuts all the path between some vertex in S and some vertex in T, then it's not that hard. And also we can do it if it's only 2 terminal pairs. And in 2015, Marcin and Magnus also proved that if we have at least 4 pairs, then it stays hard. So there's nothing we can do when we have at least 4 pairs. And until now, the 3 terminal case was just open. So we sat down actually trying to prove that it's still hard for 3, looking at the example that they constructed to prove the hardness for 4 terminal pairs. And we failed because it actually kind of works. But it's randomized, so it's only kind of. But under the conjectures about de-randomizing randomized results, we assume now it's kind of solved. So just to give another definition of the precise problem we're working for, well, now we only have 3 pairs, right? And we look for a set of vertices that we can delete such that we cannot connect any of the terminal pairs in these 3 pairs. And for the remainder of the talk, I will also use this. We'll use this set to refer to the terminals whenever I want. And the reason why these cut problems in directed graphs are so hard and stayed so hard, and why we kind of ran into this stalemate of not proceeding like 5-6 years ago with these problems, was there emerged a lot of tools for undirected graphs. I listed a few here, but it's by far from a complete list on tools for these cut problems in undirected graphs. But then people tried to transfer this to directed graphs. They noticed, okay, so shadow removal kind of works. I will explain what that is. Important separators kind of works. I will not explain what that is. But that's it, kind of. Nothing of the other things transferred to directed graphs. So they use this to solve the multicut problem, for example, but then they were kind of stuck because none of the tools actually transferred, and nothing kind of proceeded on the directed side. Until recently, the new result of Flow-Augmentation, which made a huge progress on a lot of FPT results. And I will explain a little bit what that is. So this is why now suddenly we are looking at this again and we're able to close this gap that we weren't able to close before. But Flow-Augmentation alone by far doesn't suffice to do the trick. So I'm giving a very rough overview over the algorithm. So in total it's one large algorithm that makes use of a lot of tools. And Flow-Augmentation is like only this one step here in the middle, as you can see. Not even alone, but oops, that wasn't a plan, sorry. So, but we need a lot of other tools. And the first one, as I already mentioned, is shadow removal. And then we also need CSPs. You will see we will cast our problem into a CSP along the way. Then we will notice, but we cannot solve the CSP because it's kind of still too hard. And then we use a recent new parameter twin width and reduce the complexity of our CSP to kind of cast it into something in a graph of bounded twin width on which we do model checking, which is another very recent result that we can do model checking on bounded twin width graphs. I think as Flow-Augmentation as well as the model checking of FO are stock 22 results. So, okay, but this is just the roadmap. We start at the beginning and we come back to the big picture later. We start by shadow removal. What is a shadow? So for a set X, I can define actually two shadows. The forward shadow, these are vertices that after removing my set, my start vertices cannot reach anymore. And the backward shadow or reverse shadow is, non-surprisingly, the set of vertices that after removing my set cannot reach any of the target vertices anymore. So, kind of, if you want to imagine it like this, I overdid it if my solution has these shadows because I kind of separated something I didn't even need to separate. But this, like getting rid of the shadows makes arguments easier. It's not a problem. A solution can, of course, have a shadow, right? But we kind of reduce our instance to an instance that has, if it has a solution, a shadowless solution. So a solution that doesn't have any of these shadows anymore. Actually, this is done on undirected graphs as a technique. There they do not really have like forward and reverse shadows. They just have one shadow. And they do this by random sampling of important separators, which we transfer, and then we kind of have to do this twice because we have two kinds of shadows. And but this is one of the very first and very important techniques in these type of problems, and we are happy that it also works on directed graphs. So to be a little bit more precise what we're doing, or what we're using, actually I'm not explaining how we're doing it, is we take our instance and I added to this instance very sneakily this vertex set V infinity, which are undeletable vertices. You can just imagine it for the sake of this talk to be the set of terminals. I never want to delete the set of terminals. Actually, like when doing the algorithm and applying things, this set grows a little bit, and we use this for other things as well. But for now, let's just assume it's the set of terminals and contains the set of terminals. And now I identify a family of subsets. such that if I have an input and it's a yes instance, I can find one of these subsets, and by bypassing a subset, and I will explain what that means. So if I want to bypass a vertex, I look at its in and its out neighborhood. So the in neighborhood of V, and I have the out neighborhood of V. Where exactly is it? Okay. And for every vertex from the in neighborhood and every vertex of the out neighborhood, I add the edge between them. And then afterwards I get rid of V. So I find that one of the sets I can bypass, and then I find an instant that emits a shadowless solution.
I mean, here the size of solution is k, right? So you want to delete k vertices, or
but the size, so Z in itself is not a solution. We just bypass this.
oh,
So we get rid of that. It's afterwards not in our. So we kind of reduce our instance to not contain the vertices of Z anymore, but not just deleting would destroy stuff. So we bypass them.
So after bypassing,
And then afterwards, there is a solution that doesn't have a shadow anymore.
I see.
Okay, so from now on, what you have to take away from this is that we can reduce them to an instance that doesn't have shadows anymore. Right, so I can find a solution in the instance I work from now on with that doesn't have a shadow, if there is a solution to it. Okay, so flow augmentation, that was the next step along the line. So this is a major result by Kim, Krach, Pilipczuk and Wahlström from last year. And they they give a polynomial time randomized algorithm that finds a set of edges that I can add to my graph, such that every minimal cut becomes a minimum cut between one starting vertex and one end vertex. So there's one S, one T. And I kind of add edges in, such there's no minimal cuts anymore that are not also minimum cuts. They kind of make them all the same size. And this yielded a lot of algorithmic results. The most impactful, I guess, is the one for ChainSat. And it is also, as we kind of make use of this, the only really random part our algorithm uses. So should somebody manage to get rid of the randomization in the flow augmentation, then probably you could also get, or quite sure you can also get the non-random version for the directed multicut. But we do not use exactly this theorem. We kind of adjust it. So we adjust it by using a small tool called Soybeans. A soybean is an unordered pair of two walks, and they start and end in the same vertex. So I have a start vertex, I have some end vertex, and I have like this thing, and this thing. And they agree on their start and their end. They don't have to be disjoint. If they are disjoint, we call them vertex disjoint. The ones we work with normally are vertex disjoint. And we call them CD soybeans if I have the vertices from my blue walk come from a set C, and the vertices from my red walk contain a vertex from this set. They don't have to completely live in this, they have to contain. So I have like this one vertex here living in D, some vertex here living in C, then I call it a CD soybean. So it's important I visit some vertex. And then we adapt the flow augmentation to not only give us a witness flow for our start and end vertex, but also partitioning all the deletable vertices. Remember, there's the undeletable vertices, the terminals, I do not want to ever delete them. But the undeletable vertices I partition into parts. And then I also produce a large number of soybeans for sets that are interlaced concerning these partitions of the deletable edges. So if I have a set in the partition and a path, and I look at the intersection, then I have that the soybeans walk through there. So we see this here on the picture as well. I have these two sets that alternatingly have vertices along my path, so they are interlaced. And my soybean has one walk walking through the one set and one walk walking through the other set. And of these I get a lot. Yeah. So, and this I get additionally from the flow augmentation, which unfortunately leads to the paper nearly containing a whole proof of the flow augmentation as well, because it isn't really easy to get this extra property. But the proof really doesn't do much more than doing the flow augmentation and on the side collecting these soybeans as well. Okay, so now we have the stronger flow augmentation that also gives us a flow with the corresponding soybeans for it if I put in a single start target pair. Now we change our perspective on this set of vertices I want to delete to destroy all the path connecting to, okay, if I now look at a single pair, a single start and target pair, and I look at this flow, that means that every minimum cut has to intersect all these paths. Right, so for any such flow, my set has to delete a vertex from each of these paths. And now we notice kind of, sometimes we want to talk about vertices as in the original proof, but now we have flow augmentation and rather works with edges. But luckily, on directed graphs, it really doesn't make a difference between the complexity of the two problems, whether I delete edges or vertices to separate the two sets. So we cast between the two problems at random, whenever, at liberty, I would say. Whenever we need edges, we do edges. Whenever we need vertices, we do vertices. And now, working with flow augmentation, we use edges. And now we have this space of minimal cuts. And for every flow, we have that the cut has to contain an edge from every path in the flow. So it boils down to, we have to select one of those. So we have this whole domain of edges lying in a path, and one of them I have to contain in my solution. Right, so it looks a little bit like this. I have this cut, and since it has to at least delete all of these paths, it definitely has to contain an edge of every of these. So now I can cast this into a CSP. This is where constraint satisfaction problems come up. I now make a variable for each of my paths and have as a domain all the edges along the path. And one of these edges I have to be, right? So the variable selects the edge for me. And now we can look a little bit on how the paths relate to each other and what possible combinations of variable choices we cannot have. Right? For example, if I look at these two paths here, and I have that I select x from here, and I select this y from here, and I still have this vertex before u on P1 and the vertex after y on P2, and a connection between these, then deleting x and y will not ensure that I do not have an ST path there, because I can just like walk and switch the path. So whenever I have such a connection, uv, I know that whatever I delete from P1 has to lie before u, and whatever I delete of P2 has to lie after v. Yes?
ST here are one fixed terminal.
One fixed terminal, yeah. It's all one terminal. Otherwise, this doesn't work, right? It only works for one fixed terminal. And then we get this kind of downwards closure, as we can see down here. So if I have that xy is a feasible solution, I know that I can also shift the vertex on the lower path further to the right and the vertex on the upper part further to the left. And the complicated part is that I also want to be consistent with the choices the other pairs make, right? Because I do get such a CSP formulation for every of my pairs, because I only have this for one. And the other pairs have their own variables and their own paths. And now I want to make sure that whenever I choose a path, a vertex on both paths the same, that I want to represent this in my CSP. So I get constraints that span, I cannot draw them because they are between different pairs, but I get constraints between these. And these are the ones that make it complicated. Right, now I want to look at how complicated is this constraint satisfaction problem that I get. So I make it a permutation CSP, represent all the constraints as matrices, and look at what is the grid rank. I will explain in a minute why we consider the complexity as grid ranks of matrices, but you might already guess. So, and I get that the consistency and downward close constraints, they are bounded and I'm fine, but the permutation constraints, those are harder. For those, I do not have that they have a bounded grid rank yet. So I need to reduce the complexity, and this is where we come to our irrelevant vertex technique. So we want to find vertices that I can delete to reduce the complexity of these constraints. So I want to find vertices that are definitely none of my solutions, so that I can delete them. If I delete them, the state, whether it's a yes or no instance, doesn't change. And for this, I look at two paths between two different vertex pairs. Right now I have at the top a path from S1 to T1, and on the left a path from S2 to T2. And now I have the constraints considering which of these are the same. So I look at this as a huge matrix, and whenever I select a vertex that is on both of these paths, I add a 1 into this matrix. And this gives me, as I have large grid rank, a large grid minor. Whoever does structural graph theory, this is not the grid minor you think of. So if I have a matrix, a grid minor is of order k, as if I can divide this into k sets of columns, consecutive sets of columns, and k consecutive sets of rows. such that in each of these I find a 1 somewhere. I drew a vertex here instead of a 1 because I kind of wanted it to have a name. And in our case, these are vertices, right? But in a matrix, this is a grid minor. And if I find a large grid minor, this set.
This one? No zeros?
There can be a lot of zeros.
There could be zeros, but there could also be no zeros.
There could be no zeros, but then you have a way larger grid,
Okay, yeah, just
right?
check.
So you just have to find that somewhere in this thing you find 1, 1.
Mhm.
That's enough.
Oh, so this is different from mixed minor.
This is different from.
It's different from mixed minor,
I
yes.
see.
So it really is enough that somewhere in this field I find 1 in this, then I call it a grid minor. So assume we have a large grid minor, and now I take this middle vertex, right? So I have a lot of the left, a lot of the right. These fields here now, these here, they represent these fields here. So in each of them I find a 1. And I take the 1 right in the middle. So there's a lot to the left, to the right, to the top, and to the bottom. So I distribute these parts of my grid minor into these 4 quadrants. And now it comes into play that we said, okay, if you have a solution, it's shadowless. So I know everything kind of still reaches a target. Everything still is reachable from some source. So as I'm in the beginning, in the top left quadrant, on something that are vertices that lie along a path that is reachable from S1 and reachable from S2, because they lie on both of these paths. I know that it cannot be, that it doesn't reach T1 and T2 because we have this solution, otherwise I get a path that is left over. So I know that they do reach T3. And for similar reasons, I know that in the bottom here, I have that all the 1s in here are reachable from S3. And then I have certain non-reachabilities for the other 2. I know that I'm not reachable from S1 in the top right corner, and I do not reach T2. And the other way around in the bottom left quadrant. And now we look at columns, one on the right, one on the left, of V, and select sets alternatingly, vertices alternatingly from the 2 sides from this one column I fix. So I fix the column to the left and the column to the right, and now from the lower quadrants, I take an orange vertex on the right side of V, here, so lying on P1 after V, and then here lying on P1 before V, and then again from the right, and so on. And along P2, they now lie in this order. Orange, purple, orange, purple, orange, purple. So they built an interlaced set on one of the flow paths from the Flow-Augmentation solution for the second solution pair. So I know that I find soybeans over these a lot. Not for necessarily every pair of vertices, but I can find a lot of these. And similarly, I can select a row over V and a row under V, right? And I pick a row that does contain such a vertex that's part of some soybean. And I find a similar soybean. And as I have a lot of soybeans for both, I find a vertex that lies in a soybean for both. Right? I cannot guarantee this for all of them, but I didn't want to draw a lot of vertices into the picture. So, but I can find some vertex that does lie in a soybean that I can reach from this bottom vertex, and that can reach this top vertex up here. And now I need to show that I can actually reach this vertex from S3. And I know you explained it to me, but I'm obviously too stupid to use it anyways. Okay, so here. So we can reach from here to T3. So we see that if we now combine the path of these two soybeans, I can reach from S3 to this vertex in my column and row intersection and up to the vertex that then reaches T3. So if I choose from P1 and P2 V to destroy P1 and P2, then I'm left over with a path between S3 and T3, which in the technical details of everything we prove to be disjoint from right? But so the soybeans are actually, because they are in this certain partition of things, and so we find this path that we are not allowed to have. So we know V cannot be part of our solution. And then we delete V and continue and do this again. So in the end, we obtain that we delete so many vertices that in the end this grid becomes small enough for the permutation constraint also to allow low grid ring. And then, this is why we looked at low grid ring to begin with, we look at its connection to twin width. Because if we look at a graph of bounded twin width, then I know the adjacency matrix of that graph has to have bounded grid rank, and the other way around. This means that if I look at the graph I get from the adjacency matrix, if I look at the 0, 1 matrix I got from my CSP as an adjacency matrix of some graph, that graph will have bounded twin width. Yes?
Couldn't the graph of bounded twin width be complete graph?
Yeah, I think the question is the grid rank of the full one matrix might be high, because I mean this is not mixed minor, right? It's a grid minor,
Yeah.
so
Yes.
So the grid rank of the n by n's one matrix should be n, right?
But we now have a very sparse matrix, right?
So why is it sparse?
but twin
Because we got rid of all the it's now mainly zeros, right?
yeah, maybe Kevin's question is this form of the theorem might be slightly incorrect
Oh,
Yes.
because it's a
The way you define the grid minor there says you only need a 1 in each box, but
Yes.
the grid minor for twin width needs a 1 and a 0 in each box.
Yeah, this is the mixed minor.
that okay.
I mean, it's still fine, right? If you have small grid rank, you must have small twin width as well.
Yes, that's,
Yeah.
I'm
One
sure
direction
what
will
we
be
use
fine.
is
Yeah.
correct. I'm very sorry if the precise statement here is wrong.
It's probably just the if and only if the path is wrong.
Yeah.
So,
Yeah.
There you go.
But the correct implication holds.
Okay. I'm very sorry,
That does it.
especially to the twin of people. Yeah, but important is that we can now cast this to a graph that has bounded twin width. As long as you believe that direction, then everything is fine. So, because now we look at this graph, but we said we have to do model checking, so now we also have to cast the whole CSP into a formula, right? So we take the CSP constraints, make them into this graph of bounded twin width, and make produce a formula that goes through the constraints and evaluates this on this graph to 1 exactly if it yields a solution to our CSP. And as the graph now has bounded twin width, thanks to this, we can use the result from Bonnet, Giocanti, Osona de Mendes, Simon Thomas, and Turunchik to prove that we can do this model checking task in FPT. So the formula I mainly don't explain because it's boring. It goes through the constraints and describes how this constraint looks. And the graph you get by taking the adjacency matrix here. Okay, so now we have this CSP that we can now check whether it has a solution or not, which finishes the whole journey around a lot of tools. So to recap, in the beginning we split into several instances kind of on this family of sets. There's one I can delete to get a shadowless solution, so we just try all of them. Then for each such new set of instances, I kind of do this flow augmentation 3 times, getting 3 flows, sets of arcs I add, and then kind of casting them all together into one large CSP, which has these 2 types of constraints that are only specific to the one terminal pair, and this one type of constraints that actually relates the terminal pairs, which holds most of our complexity, right? Then we go and reduce the complexity of this to make it into some new graph and a formula that we can then do the model checking on. We actually, because a lot of these tools were used for weighted proofs a lot, we were asking ourselves whether we can do anything about then weighted directed multicut. The answer is no. Because for the weighted directed multicut, it turns out that you can transfer the hardness proof that for the 4 terminal pairs to the directed version by kind of coding the problem of 4 terminal pairs into the weights instead. So then you only need 2 terminal pairs. It's hard for even 2 terminal pairs. So no, we can't also do this for the weighted version. But in the end, I still think we take away a lot, even if we didn't introduce a new tool. But this way of doing bounded twin with CSPs has not been done in this combination before. So this might also be useful for other problems, because it's not specific to how we got the CSP in the first place. The reduction of the complexity of the CSP, however, is very problem specific. So if you want to use something with bounded twin with CSPs, you have to probably find a different way to reduce the complexity of the CSP. But I think it's a promising way to use this twin width model checking result for problems that are easier, maybe even way more natural, considered as a CSP than a directed multicut is. Because I guess for the directed multicut to see this, we needed the flow augmentation to happen first. I think otherwise we would probably not have come up with the idea of coding this into a CSP. But the flow augmentation kind of makes this a kind of natural thing to do then all of a sudden. Yeah, the Soybeans are a rather technical tool. I'm not sure whether you can find other application to it. But maybe in a similar way, maybe you can people can come up with this. But also I think adding the soybeans to the flow augmentation as a variant is maybe the more interesting idea. So you can prove variants of the flow augmentation, stronger variants that are more more related to your problem, or give a slightly stronger, for your problem very relevant property. But it's a little bit hard to prove these, because it's hard if you want to like the just slightly stronger property to get around proving the whole thing to begin with all again, which we kind of didn't. So I guess then you would have to also do this. But this whole like combining these tools, I think, is the more interesting result, next to, of course, closing this gap that we were very, very happy to finally close. Okay, that's it from me.
Thank you. Questions?
Yeah.
So where does the proof actually use that the number of terminal pairs is less than 4? I think I missed it.
For these permutation constraints, because you, if you have, so that you get this path from S3 to T3 via the soybeans, that doesn't work if there's not only this one starting vertex and only this one end vertex to connect.
Okay.
Because as soon as you have 4, you might end up with a path from S3 to T4, and then that's totally fine, and, right?
I see. So you're eliminating 2, and then there's 1 left over, so it has to be the right.
Exactly.
Okay. That's
Yeah. So this is very definitely used that there's only 3 terminal pairs.
After the very first step, you split into many instances, right?
Mm.
For this, you need a bound on the size of this curly set.
Yeah.
Maybe I missed it. Was the bound in the statement?
I hope so, but there is a bound on this.
There was a bound on running time.
Yeah,
so
I remember the running
we
time.
can only output
I guess, yes.
Yeah, I didn't give the bound on that. There is a bound on that.
Yeah.
I'm sorry, yeah.
I have a question too. So probably this must be true. In general, we don't know how to find these contraction sequences. Even if you have an instance of small twin width, we don't have a general algorithm to approximate these decompositions, right? So
Which decomposition?
like for the twin width.
Yeah.
So for tree width, if we know that the input has small tree width, then we know how to find the decompositions. So we can use it to do the model checking. For twin width, in general, there's no such algorithm known, right? But in your case, is it true that because of this grid minor thing that you can immediately get the twin width decomposition,
The
these contraction
decomposition?
sequences?
I guess it's an ordered matrix, right? Because you're along these two paths.
Yeah,
And
it's
I
not
think
a
if you
matrix.
order it, it's fine, right?
So it's a grid, just since you already have ordering, so is that
Yeah.
so just greedily contract consecutive pairs in the matrix.
Yeah, I guess.
And also, I was wondering whether, I've never seen this irrelevant vertex technique being used for anything other than tree width or branch width. Is this first instance that you know?
Oh, that's a good. It's the first I know of, but I'm also working with tree width stuff a lot. So
Yeah.
all the irrelevant vertices I know. I wouldn't be surprised if some people use something like this for irrelevant vertices before. I don't think that's like a major new idea of ours. I'm just not aware.
I think the directed disjoint path problem for planar graphs uses irrelevant vertex without tree width.
Yeah.
Mm.
Yeah, maybe. But then via a planar structure, right? Yeah, so planar structures, that's true. Those you could count as not tree-width related, I guess.
So I guess people previously must have tried to reduce the directed tree width, right, by removing something instead of.
Yeah.
I mean.
Yeah, for tree-width, I guess it's definitely the first and the most known one, right?
Yeah.
For irrelevant vertices. Yeah, I think the irrelevant vertex one it's not super new.
Any other questions? If not, let's thank the speaker.